I don't want to repeat the introduction, but I'm a general surgery registrar in Newcastle, currently doing a PhD, and a large portion of my PhD is creating artificial intelligence algorithms. And so I've been invited to give a talk about artificial intelligence in organ transplantation, and I'm trying to make sure that I try and address it in a fair and interesting way. So the things that I plan on doing is give a brief introduction on what AI is and what it's not. I think we all can have we all intuitively know if something is AI nowadays, but I think it's a little bit more difficult to know when it's not AI, and that can have implications with regards to how we understand and engage with this technology. I then want to outline some examples of AI in transplantation, and I'll look at some examples that have come from UK research institutions, and over there I'll take some time and tell you a little bit about the research that I've been doing during my PhD. And finally, I'll talk about some reflections around the challenges and opportunities of implementing AI in transplantation and more generally. But above all, I also want us to have some fun. So there's going to be some silly images and GIFs along the way to make sure that everyone stays awake and doesn't fall asleep listening to me speaking. So let's start with a fundamental question of what is artificial intelligence? What is AI? I think I've got a bit of a love-hate relationship with the word artificial intelligence because it's such a broad term. It's a broad umbrella term, and that makes it very difficult for us to have informed and nuanced discussions around this topic. And the examples I sometimes give around this is to think of another word which is also very broad. And that word, for example, can be medicine, right? Medicine encompasses a lot of different things in it, like surgery, medicine, like physician medicine, public health, vaccinations, etc., etc. And many of the things in medicine are taken for granted. Some things within medicine can be controversial. It can lead to sometimes heated discussion. So medicine as a general word is rarely used to describe something that is being done. So to give another example, if I were to create the sentence or put the sentence together that medicine is going to revolutionize organ transplantation, most people would say, hang on a second, what do you mean exactly by saying, that medicine is going to revolutionize transplantation? Which part of medicine exactly? But we do it every day with artificial intelligence. As we heard earlier, almost every day there's a news article talking about how artificial intelligence is going to revolutionize every aspect of our lives. And so I think it's important for us to have a better understanding of what is underneath this umbrella term. And I wanted to do that when I started my PhD about just shy of 3 years ago. So I went and looked for definitions. And unfortunately, most of the definitions are not very useful because they're fairly circular. They essentially describe computer science algorithms that do intelligent things. So if we're describing intelligence by saying that it's a computer that does intelligent things, we're not really left with, we're not any closer to the answer of what is it really that makes computers intelligent. So the question really becomes not what is artificial intelligence, but if we really want to answer this question is what does it mean for a machine to be intelligent? And when I was trying to really, do a deep dive on this and answer it in a way that, or learn it in a way that isn't just learning a definition by heart, I thought about computers when they weren't intelligent. Let's think about computers at a time where they were definitely not intelligent. And that takes us back to the 40s and the early 50s, where essentially computers were these massive calculators. They took up the size of a room. And what they were very, very good at was performing calculations. So they could scale and do mathematical computations at a speed and at a pace that humans couldn't do. And so we've got here an example of the world's first programmable electronic digital computer that was built in Britain in the mid-40s, and its job was to helped in the code-breaking efforts in World War II. And this is a computer. This is not an artificially intelligent computer. It can do something that I would argue required a lot of intelligence, right? Doing all those computations requires intelligence, but it doesn't entail artificial intelligence. And the reason for that is that humans still had to do quite a lot of work. Humans had to write the programs that would then be given into these computers, and the computers were essentially bespoke to that program. The computer could only solve one problem. If a different problem had to be solved, the wiring had to be changed, the computer had to be remade. So let's imagine ourselves in the year 1946. The Nazis have been defeated. We no longer need this computer to break code, but we'd like to use this computer to, for example, forecast the weather. Well, we can't just go and ask the computer scientist to write a new program. Everything needs to be redone. And so the computer scientists of the time, some of the brightest minds, starting with Alan Turing in 1947, he first described this concept publicly. The concept came about of, can we create machines that can actually learn from experience, and machines that can alter their own instructions? So in other words, the year is 1947, we've got computers that can do a lot of calculations, but there's still a lot of other work that needs to be done for these computers to actually do what we want them to do. And that is the realm of what we describe as artificial intelligence. So 10 years later, just almost 10 years later, the 10 brightest mathematicians and computer scientists at the time met in Dartmouth in New Hampshire in the US, and they described, and they coined the term artificial intelligence. So they described the problem of artificial intelligence. And they meet for 2 months to solve this problem, which in their words is that they want to be able to stimulate intelligence. So their hypothesis is that if every aspect of learning or any other feature of intelligence can be so precisely described that a machine can be made to simulate it, then we can create intelligent machines. And here we are, 69 years later, after this meeting, where we've got these expanding data sets with a lot of information. We've got maturing AI technology. So again, the mathematics and computer science that's required to deliver these artificially intelligent machines, or to simulate the intelligent processes that aren't just a matter of calculations. And we've got these incredibly powerful computers now that can take the data and take these formulas and put everything together. And here I've got an example of what AI is, as opposed to a simple calculator. So over here, I took a piece of paper and I wrote on it, what is the square root of pi? I took a picture of that and I uploaded it onto ChatGPT. ChatGPT was able to take as input a picture, right? This isn't text that I have given to it. It's an image. It's been able to identify that in the image there is writing. The writing is in English. There is a math problem in that writing. It's able to decipher my own handwriting. No computer scientist has sat down to decipher my own handwriting and write a custom program that can take George's handwriting and turn it into a computer readable text. That is all the result of machine learning. And within a few seconds, it can take this image, extract the information, and actually create a calculation. And that is obviously very different to what it would be like to just use a calculator, where the calculator would execute a fixed, predefined set of rules and formulas. It would require very specific input, right? I can't just put anything. The calculator tells you what will accept as input. And it can't learn from experience or learn with more information. A calculator will always remain that calculator unless it's been reprogrammed. Right, that ends the bit about what is AI. I hope I've cleared the water rather than muddied them even more. And now I'll talk about some examples about AI in organ transplantation. Again, AI is a huge term, right? Huge umbrella term. And I think that the three main areas of artificial intelligence that we think about when we talk about AI in organ transplantation are machine learning, computer vision, and various generative AI computer programs that include natural language processing. Um, Primarily, we think about machine learning algorithms that are capable of taking these large data sets that we have and being able to identify information in that data set to help us optimize the care that we deliver. So in terms of machine learning, there are plenty of tools that look at how we can improve the prediction of patients in transplant outcomes, how we can improve organ matching and the allocation of organs, and how we can optimize post-transplantation care. With the example of immunosuppression therapy, we don't want to give too much immunosuppression where we end up with the side effects, but we don't want to give too little immunosuppression and then risk a rejection. Now, if I were to try and speak about all of the different examples of this research, I think I would need a week. I need a lot more than an hour. But I'll speak about some more detailed examples. Again, I've got three examples, two brief, one in a little bit more detail, which is my research project. So the first example that I've got here is a machine learning example. So researchers in Oxford, led by Professor Simon Knight, have done quite a lot of work at investigating whether these machine learning algorithms can help us improve the prediction of transplant and patient outcomes following kidney transplantation. But importantly, and the reason that I've chosen to show this is that they're also implementing explainable AI algorithms. And that allows us to peer inside the so-called black box of artificial intelligence. A lot of these algorithms are so complicated that you give them some data, they give you an output, they give you an answer, but it's impossible to really tell what's happened inside or which bits of information were the important ones in making the decision. And having explainable AI is the availability of explainable AI gives us a tool to peer into that and to get some explanations. Next, I've got an example of a computer vision work that's been carried out in Cambridge under the supervision of Professor Pettigrew. And over here, we've got AI that is capable of taking visual information and helping the doctors that look at the samples of organs under the microscope to more easily measure the areas of interest and get the information that we need from those biopsies in a quick, fast, and reproducible manner. And that leads me on to my PhD and my work with the ORCA project. ORCA stands for Organ Quality Assessment. And this is really a project that combines the two. So there's definitely computer vision elements in it, but there's also machine learning elements in it. And I'll go into them over the next few slides. Our ultimate hope here is that we can increase the number of transplants that are being carried out, primarily in the UK, but also in the world if these models externally validate. So the problem we're trying to address is that at the moment, the number one reason for which organs are donated, retrieved, and then not transplanted is the visual assessment of these organs. And it comes down to concerns around the quality of perfusion. So how well does fluid go into the kidney and flush out the areas of the kidney? And for livers and pancreases, it's the fatty appearance of the organ. The more fatty an organ is, the less likely it is that it will work in a recipient if it's transplanted. And so, transplantation only really works and provides a benefit if the transplanted organ functions. And so we need to make sure that we that we are safe in our organ utilization decisions. But we know that these assessments are subjective. There's inter-center and inter-rater variability. And in providing an objective and reproducible tool that can help in the visual assessment of these organs, we believe that we can help reduce this variability, increase the overall number of transplants, and also help make access to transplantation more equitable through the different centres in the UK. So the premise here, the idea is that we can use computer vision algorithms, specifically convolutional neural networks, and we can train them to create a quick and reproducible and objective organ decision aid tool. The idea here is that we want to assist surgeons in making their decisions. We don't want to replace them. There was quite a lot of work done at the outset of this project. Discussions were had with patient and public involvement groups, and the piece of feedback that we kept getting again and again and again was that any AI technology that is being developed should act as an aid and shouldn't act as a replacement for the clinicians and the patients. And so this is something that we have taken forward and essentially made sure that the algorithm doesn't, or the application, when someone interacts with it, it doesn't give you an answer of transplant or don't transplant or good quality or bad quality. Instead, it gives you a score that ranges from 0 to 4, and it's up to the clinician and the patient to make a decision on what that score means to them and how they want to implement that. In terms of the methods, we had a large collection of images of livers that were donated, and then we asked 12 different consultants from 8 different centres across 3 countries to give their opinions about how fatty these organs appeared. We then collected these opinions. We created a consensus score, so the average of all of the opinions, and those acted as the label for the images, or the ground truth for these images. And that's where that machine learning aspect comes in. So we've got the images, we've got the labels for these images, and we let a machine have a look at these images and identify the features that mean that a liver should be in the non-mild, moderate, or severe category. And obviously that was quantified in that scale, 0 to 4, as I said. And this is an example of an organ that wasn't used in training going through the algorithm. This is a print screen of the algorithm, and over here you see the image that has been given. You have a visual sense check of making sure that the organ has successfully been identified. So your organ color here, this shade of brown changes depending on the image that has been given. And over here we can see that this brown corresponds to the average brown of the organ. And the score that we get in this case is a 0.8, so 0.8 out of 4. And broadly speaking, scores from 0 to 1 correspond to none, 1 to 2 mild, 2 to 3 moderate, 3 to 4 severe. And this maps out to the language that we currently use during organ retrieval operations. And this is how we record liver fattiness into the NHSBT registry. So anytime a liver has been donated, the retrieving surgeon needs to provide that information for the registry. So to recap, essentially what we've done is we've used machine learning and computer vision to put the eyes and minds of 12 consultants, experts in their field into an application, and through taking a picture and using that picture as an input into the application, you can get at the end a score that is what you would expect 12 different surgeons to look at an image and to give you their opinion on that image. To end about ORCA, two further things. So the future work, well, this work is happening as we speak. So the validation of ORCA, One of the questions that we get asked a lot, and one of the potential criticisms around Orca at the moment, is that it has been trained on the, as we say, subjective opinions of expert surgeons. So that is a weakness if we consider that at the moment, the agreed standard by which we should be evaluating how fatty an organ is the biopsy result. It's taking a small sample and looking at it under the microscope. So the work that I'm carrying out at the moment is to use photographs of livers that have been biopsied, for which I've also got an ORCA score, and to see how well that ORCA score matches with the biopsy assessment, so the assessment of looking at the organ under the microscope. I can't yet share all of the results, but at the moment the results are reassuring, and I very much look forward to be able to share these results in the near future. The next bit of information that we need to figure out with regards to ORCA is whether or not it will change behavior. So just giving access to this tool doesn't necessarily mean that the transplant community will change their behavior. And so Prof. Wilson, my supervisor, has recently received a grant to run a randomized control trial where 50% of livers will come with all of the usual information, and the usual information includes photographs of livers. And this is routine practice at the moment. We do that so that remote teams can make informed decisions around whether or not they want to accept and utilize an organ or not, or whether or not they want to stand down and allow another center to accept that organ. And so, yeah, 50% of livers will come with that usual information. The other 50% of livers will come with the usual information plus with an ORCA score. So the images will have gone through an algorithm, and when the surgeons look at the images, they'll also be able to see that score ranging from 0 to 4, and that will give them some objective information around the fattiness of the organ, and they don't need to rely entirely on subjective opinion. Right, and that brings me to the last bit of my presentation. These are the reflections on the challenges that lie ahead. As I alluded to earlier, I mean, problem number one, I think, for a lot of people in a lot of people's minds is the black box problem. These algorithms can be quite complicated, and if we don't know why it's made a decision, then that can lead to issues with bias, with who is responsible if something goes bad, and you know, if it is the human that's responsible, which I think it should be, then how can the human trust the algorithm, right? And how can they be informed in making their decisions, and making their decisions on the basis of whatever an AI algorithm might have given them. And I think the antidote to this is the field of explainable AI. So there's an entire field within artificial intelligence which is dedicated to creating algorithms that are essentially add-ons that can be used after you've trained an algorithm, and then these add-ons can actually look inside of the algorithm and try and figure out which pieces of information or which areas in an image were the most important in that algorithm, giving you the decision that it's given you. And that exists for both tabular information, the usual information like an Excel sheet, and visual information, such as the examples that I've got here. So Excel sheet, tabular data, we've got sharply edited explanations, and for visual information, we've got CAMS algorithms, which stand for class activation maps. Another problem is if we don't trust the AI, and one of the sources of not trusting AI is that they don't like to say that they don't know. I have never asked ChatGPT something and it's turned around to me and said, sorry, don't know. It will either make something up, or sometimes it tells me that, it doesn't want to tell me. But it never says that it doesn't know. And when it makes things up, it's very, very sure of itself. It's very certain of itself. And ultimately, I think at the end of the day, it's because we need to remember that AI is a technology that has been built to try and probabilistically come up with a sentence or a paragraph or a piece of code, if that makes sense. The reason that most of the output is true is because, generally speaking, true things have been written. If ChatGPT was trained on data set that was all lies, then it would lie all the time. And it would lie in a very predictable way, that it would lie in the way that the data that we gave it lies in. We need to keep that in mind. And another source of mistrust that recently has been coming about is the fear of de-skilling and the fear of never skilling. So that there's fears now, or there's concerns that physicians that are being trained at the moment. So if you're a medical student today and you're going through medical school, and then you'll go through your medical training, that you might never skill to the level of clinical skill that someone that was trained before AI. Now, I don't think that concern is entirely accurate. I think that there are ways that we can implement AI to assist training and to help training and to make sure that training is reflective and maybe more customized. But these are definitely things that we need to be thinking about and discussing as we progress into the future with this technology. Now, the antidotes, I think, to AI not being trusted, as I said, about hallucinations as an example, or whether or not we're skilling or not skilling. I think number one is education, being AI literate. Whether we like it or not, this technology will be important in the future, and we need to be active citizens and active scientists, and we need to learn enough about it to actually be able to engage with it in a critical way, in a nuanced way. And the other thing is that we need to make sure that the regulations that are being formed at the moment are fit for purpose. So as clinicians and scientists, we rarely like the work of regulation, but we need to be actively involved in this as much as we can, and try and read about it and understand about it, because otherwise decisions will be made without our opinions being taken into account. Another thing I want to say, and potentially this should have been the first slide, is that at the end of the day, data is supreme. So just because we've got really, really modern and flashy and new AI machine learning models to use, and there's a new one that comes out every week, if your data isn't good, the model won't be able to work. So AI isn't immune to the problem of garbage in, garbage out. And so we need to make sure that we curate our data very well, that we try and know our data well, and that we don't just rely on the brilliance of AI. Otherwise, we may end up, as I said, with garbage in, garbage out. And just because we've got this label of AI on it, we erroneously put our trust on those systems. And this is the last set of slides, and it's around the topic of how fast progress is being made in this field. And I think at the moment there's a lot of hype. There's a lot of people out there, especially people that are trying to sell products in artificial intelligence. And every 6 months we hear that the general artificial intelligence that will be able to solve all problems and lead to world peace is 6 months around the corner. And then 6 months around the corner comes, and we're not quite there yet. There has definitely been a huge leap between 2020 and today. But the progress of AI has always come in leaps and then plateaus and leaps and plateaus. And the future isn't certain. Another example to visually show this that I've used is these two photographs. So both of these photographs are 66 years apart. So from the first flight, the Wright brothers, to a man landing on the moon, and then the Dartmouth conference and ChatGPT being released. If we expected that same fast pace of development, we'd expect that we were all in spaceships having martinis, looking at Mars. But the pace of improvement slowed, and priorities may be changed as well. So slight tongue-in-cheek next slide, but space seems to have become this place for billionaires now to send their cars or to go on 15-minute tourist trips. So what happens with AI in the future? I think it's up to us to define that. And I think being, as I said before, active citizens and literate in this field, I think will ensure that the future of AI in all of the potential benefits that it can give us are aimed at the greater benefit rather than just making people very, very rich. Right, that brings us to the end of my talk. I hope you've enjoyed the content and the silly slides, and I very much look forward to your questions. Thank you very much.